Emmy Noether stands as a giant in the world of mathematics. Her profound insights transformed the field, leaving an indelible mark on how we understand the universe. Born in Germany in 1882, Noether's brilliance shone brightly, illuminating even the most complex mathematical concepts. This essay delves into the life and work of this extraordinary woman, celebrating her enduring legacy and the impact of her groundbreaking discoveries. Noether's journey was not without its obstacles. As a woman in a male-dominated field, she faced numerous barriers, yet her passion for mathematics burned brightly, propelling her forward. Her story is one of resilience, determination, and the triumph of pure intellectual brilliance. Emmy Noether was born into a family of mathematicians. Her early life was steeped in the world of numbers and equations, a world that would shape her future in profound ways. Her father, Max Noether, was a renowned professor, sparking her early interest in the subject. Max was not just a father, but also a mentor, guiding Emmy through the complexities of mathematical theories and problems. Despite the societal norms of the time, which discouraged women from pursuing higher education, Noether's family nurtured her intellectual curiosity. They provided her with an environment where learning was encouraged and her ambitions were supported.
Initially, my path seemed set towards teaching languages. I was expected to follow a more traditional route, one that was deemed suitable for women of my time. I excelled in English and French, obtaining the necessary certifications to teach. These achievements were significant, yet they did not fulfill my deeper aspirations. However, my true passion lay in mathematics. The elegance and logic of mathematical principles captivated me in a way that languages never could.
At the age of 18, she made the bold decision to audit mathematics courses at the University of Erlangen, where her father taught. This decision marked a turning point in her life, setting her on a path that would lead to groundbreaking contributions in the field. This was no easy feat. Women were not officially allowed to enroll in universities at the time. The barriers were immense, but Emmy was determined to overcome them. Noether needed special permission from each professor to attend their lectures. Each request was a battle, but her persistence paid off as she gained the knowledge she so deeply desired. Undeterred, she persisted, her love for mathematics fueling her determination. Her journey was not just about personal achievement, but also about breaking barriers and challenging the status quo. Emmy Noether's story is a testament to the power of passion and perseverance in the face of adversity. Emmy Noether's exceptional abilities soon became apparent. She wasn't content with simply attending lectures. She actively engaged with the material, challenging established ideas and proposing new ones. Her insights impressed her professors, including Paul Gordon, a leading expert in invariant theory.
In 1907, after years of auditing courses, Noether was finally permitted to officially enroll at the University of Erlangen. She completed her doctorate in mathematics with summa cum laude, a testament to her exceptional talent. However, despite her qualifications, securing an academic position proved to be another uphill battle.
Universities were reluctant to hire women as professors. For several years, Noether worked unpaid at Erlangen, relying on her family's support. She continued her research with unwavering dedication, publishing groundbreaking papers that garnered attention from mathematicians beyond her university. Section 4. Abstract Algebra Revolutionizing Mathematical Thinking. Abstract algebra is a fascinating and complex field that has transformed the way we understand mathematics. It delves into the very essence of mathematical structures and operations, offering a new lens through which to view the world of numbers and equations. Emmy Noether's work had a profound impact on abstract algebra, which, is a field that deals with the structure of mathematical objects and operations. Her contributions were not just incremental, they were groundbreaking, reshaping the landscape of mathematics in ways that are still felt today.
Prior to Noether, algebra was largely focused on concrete examples and specific calculations. Mathematicians would often work with particular numbers and equations, solving problems on a case-by-case basis. This approach, while effective for certain tasks, limited the scope of algebraic understanding.
Noether's approach was revolutionary. She introduced a level of abstraction that allowed mathematicians to see beyond individual problems and recognize underlying patterns and principles. This shift in perspective was akin to moving from a two-dimensional view to a three-dimensional one, revealing a richer and more intricate mathematical landscape. She shifted the focus to abstract structures and general principles, paving the way for a deeper understanding of mathematical concepts. By emphasizing the importance of these abstract structures, Noether enabled mathematicians to develop more general theories that could be applied across a wide range of problems.
One of Noether's key contributions was the development of the theory of non-commutative rings. This theory challenged the traditional notions of algebra and opened up new avenues for exploration. It was a bold and innovative step that demonstrated Noether's deep understanding of mathematical principles.
In simple terms, a ring is a set of elements with two operations, addition and multiplication, that follow certain rules. These rules help define the structure and behavior of the ring, providing a framework for understanding its properties. In a commutative ring, the order of multiplication does not matter. This means that the result of multiplying two elements is the same, regardless of the order in which they are multiplied. This property is familiar to most people from basic arithmetic.
Noether's work explored the properties of rings where the order of multiplication does make a difference. These non-commutative rings are more complex and require a deeper level of understanding. Noether's insights into these rings have had a lasting impact on the field of mathematics.
This might seem like an abstract concept, but it had far-reaching implications. The study of non-commutative rings has led to advancements in various areas of mathematics and has provided new tools for solving complex problems. It has also influenced other fields, such as physics and computer science, where the principles of non-commutative algebra are applied in innovative ways. Noether's work on non-commutative rings laid the foundation for many branches of modern mathematics, including algebraic topology, representation theory, and algebraic geometry. Her legacy continues to inspire mathematicians today as they build upon her groundbreaking ideas and explore new frontiers in the world of abstract algebra. Section 5, Noether's Theorem, a bridge between symmetry and conservation laws. This theorem is a cornerstone in the field of theoretical physics and mathematics, providing profound insights into the nature of our universe. Perhaps Emmy Noether's most famous contribution is Noether's Theorem, a fundamental result that connects symmetry in physical systems to conservation laws. This theorem has far-reaching implications, influencing various branches of physics and mathematics, and is considered one of the most beautiful results in theoretical physics.
In physics, a conservation law states that a particular measurable property of an isolated physical system does not change as the system evolves over time. These laws are foundational principles that help us understand the behavior of physical systems, from the smallest particles to the largest galaxies. For example, the law of conservation of energy states that energy cannot be created or destroyed, only transformed from one form to another. This principle is crucial in understanding processes such as chemical reactions, nuclear fission, and even the functioning of stars.
Similarly, the law of conservation of momentum states that the total momentum of a system remains constant in the absence of external forces. This law is essential in analyzing collisions, rocket propulsion, and the motion of celestial bodies.
Noether's theorem provides a deep and elegant explanation for these conservation laws. It bridges the abstract world of mathematical symmetries with the tangible laws of physics, offering a unified framework to understand the conservation principles. It states that for every continuous symmetry in a physical system, there exists a corresponding conserved quantity. This means that symmetries, which might seem purely mathematical, have real, observable consequences in the physical world.
In other words, if a physical system remains unchanged under a certain transformation, then there is a corresponding physical quantity that is conserved. This profound insight not only deepens our understanding of the universe, but also guides physicists in their quest to uncover new laws of nature. Noether's theorem continues to be a guiding light in the exploration of the fundamental principles that govern our reality.